Hi everyone. I'm going to go into vector clocks and what they tell us. I'm going to explain some of the theory behind it at a surface level, so you can understand the basics. I'm doing this because I believe if you understand the basics to something like a vector clock, you can kind of get a deeper understanding of the details when you try to read this paper. Um, because like these are really not super easy to understand since they're kind of a step forward from what you know about Lamport clocks when you watch this. So why do we need vector clocks? What's even the point of them, right? We have Lamport. Is that not enough? Well, we need them because they can simulate a synchronous distributed system on a given asynchronous system. So it kind of lets us know what's happening more per process or per node or per machine, whatever you want to say, more than what like a traditional Lamport clock can. They can help simulate global time, like with this happens before, happens after late relationship that we'll dig a little deeper to later. And they can simulate global state. So kind of the same concept of global time. It's just a global state, and we'll also go into that a little bit more in detail coming up here. So, what are some possible ways that we can simulate this global time or global state before we hop into vector clocks? So, the first approach is kind of called a synchronizer, which simulates clock pulses in a way that a message is only generated at a clock pulse and will be received before the next pulse. A synchronizer is typically intended to be used as an additional layer of software um, on top of like an asynchronous system. However, the message overhead for something like this is rather high, so the people tended to stay away from it. Lamport clocks, that's one way we can kind of synchronize systems, but as we know that they can't give us any sort of guarantees outside of, you know, something happened before something else. Uh, the third is a snapshot algorithm. This can be effective in like kind of capturing state, uh, or can elaborate the idea of leading to characterization of like this concurrent common knowledge. But all of these kind of have some sort of lacking where we need some understanding. So vector clocks are great to kind of fulfill those needs we had in the last slide. Their linearly ordered structure of time is not always adequate for distributed systems, but they allow kind of a partially ordered systems vectors forming a like kind of a lattice structure. You'll see they're kind of like imagine you have three nodes. Each node has a list of three elements that are basically clocks per element. Um, and I'll kind of go into this a little bit more depth. So here we go. So what a vector clock is? So basically, for every node, uh, there's a digit within a list representing the current event count, kind of like what I said. And events are atomic actions which occurred at the node or process during ascend, an internal process, or receive. So like if you can look at this diagram, right, we see P0 does its own, like maybe it increments something. Now it's 100. Um, then it sends an event, so it's 200, and it sends it to P1, which has done two events itself. So when P1 receives its clock, it actually changes it to 2-2 to correlate um, with the events it's received. It's basically like a Lamport clock with the same rules of overriding digits, but kind of in like a list format now. That's how I kind of like to think of it. Um, So what do vector clocks even tell us? Like, what's the point? Well, they give us this causality ordering, which is A happened before B or B happened after A, which is big because Lamport clocks can only guarantee A happened before B and not the other way around, I believe. I might be mixing that up, but Lamport clocks can only guarantee in one direction, whereas vectors can kind of give us this guarantee in both. So, like, an example of something that would be a violation of causality ordering, this little fun diagram I drew, is Alice tells Bob and Chad, or Charles, however you want to think of it. We'll say Chad in this example. Alice tells Bob and Chad that I hate you. And they're in a group chat, right? So Bob gets that and immediately says back, Alice, you're horrible, right? And then he sends that also to Chad since they're in this group chat. And Chad sees that Alice is horrible. And then Alice says, I hate you, right? So to Chad, he thinks Bob started it, when in actuality, Alice started it, but he got the message later. So this is a causal violation. So this is kind of what vector clocks are meant to prevent. And that's why people like to use them. So there's a concept in vector clocks called cuts, and they're they're a little difficult to understand at first, but as you kind of see them more and more, you'll kind of understand them. So if a process sends messages to all other processes in order to initiate local actions or recall some distributed information, uh, these messages will usually be received at different time instances. Due to unpredictable message delays, it is not possible to guarantee that all local actions triggered by the messages are performed simultaneously. This motivates the notion of a cut. So the cut is like this kind of zigzag looking line in a time diagram where it cuts it into two parts, a left part and a right part. A cut is kind of, in other words, is a subset of global history that contains an initial prefix of each local state. So it kind of, the left side is a past, the right side is a future, and this basically allows us to tie causality to these cuts. So if you look at this definition I have, you'll kind of understand it. They're very difficult to explain, so I'm having a little trouble explaining. So hopefully in the next slide it'll make a little bit more sense. Um, so there's something called consistent cuts. So so easy, right? A cut is a consistent if every message received was sent. Now, what the heck does that mean? So in other words, a cut is consistent if and only if for each pair xy, right? Uh, y is in the cut and x happens before y. So we can see here that in this little example that I have, the left side of this time diagram is a consistent cut because you can see H is in the cut and H caused F, or era F, whatever it means. And then an inconsistent cut violates one or two or both of or one or both of those things. So G did cause D, but only D is in this cut. So that's an inconsistent cut. So you may ask, like, why do we even need consistent cuts? Like, what's the point? Well, they're really good for global state. So all cut events of a consistent cut can occur simultaneously, and there's a potential execution of distributed computation in which all cut events indeed happen in real time. A snapshot of these local states of all processes taken at the same time is obviously consistent. Therefore, the global state computed along a consistent cut is correct. The global state of a consistent cut comprises of the local state of each process at the time the cut happens, and the set of all messages sent but not yet received. In the time diagram, these messages are characterized by arrows crossing the cut line that we saw in the last slide, right? From left to the right side. So this global state kind of helps when you're trying to solve the snapshot problem, which consists in designing an efficient protocol which yields only consistent cuts to collect local state information, right? If you're like have a distributed database or a distributed system and you need to take a snapshot for a backup, you want that snapshot to consist of consistent cuts and you don't want inconsistent cuts. Otherwise, when you try to restore from that backup, things might not be as they should have been. So we've talked a lot about vector clocks and like how they help with causality and time and everything. So what exactly is time? Well, time is hard in distributed systems. You guys all know this. The hope is an algorithm where global time is available to all processes, right? If everyone had the same global time, we wouldn't have to do all of this clocks and synchronization and stuff. Everyone would know the time at every given time, but you can't do that because of, time drift and latency between different processes located in different parts of the world. So that's a hope, but that's difficult to do if not impossible. A clock synchronization algorithm realizing virtual time as a suitable approximation of global time, right? So if we can't get this true global time, we need to have an algorithm that can simulate this sort of virtual time, right? And the main difference between virtual time and real time seems to be that the virtual time is only identifiable by a succession of events. So that's what we're talking about in terms of vector clocks, right? So virtual time does not it's basically just doing nothing and waiting for virtual time to pass. Like, what am I trying to say? So by not doing anything, virtual time does not proceed, right? Virtual time happens when an event is triggered, either like we had when you're internal, receiving, or sending an event. So keep that in mind when you are thinking about what virtual time really means. It's only a succession of events, not an actual, timestamp. So vector time, right? As in Lamport original scheme, each message gets a piggybacked timestamp consisting of a vector of the local clock. By receiving a timestamp message, a process gets some knowledge about the other process's global time approximation, and the receiver combines its own knowledge about global time. So, like, right, you can kind of see what's going on here. Another important thing is a process will always have the most up-to-date information about itself, right? Because it's whenever it triggers its own event, that's the most up-to-date. So you'll kind of see, like we saw earlier in those graphs, you have 4 nodes, right? Everyone has 4 nodes of global time, and uh, they kind of update each other based on when events are passed around. So some summary to kind of what I just went over, because trust me, I know it's a lot and it's difficult to understand, but the more you look at it, the more it'll make sense. So a single vector clock might not know about node states if they have no communication with each other or through mutuals, right? So let's say we have Alice, Bob, and Chad. If Bob and Alice never talks to Chad, they won't know what his clock is, right? Fairly obvious. However, if Bob talks to Chad and Alice talks to Bob, Alice will have an approximation of Chad's state, right? Because Chad's state could have changed in between Bob and Chad talking. So even if Bob recently received updates from Chad, Alice cannot tell from looking at Bob's vector clock if Bob got his new clock values from Chad or if Bob was already aware of his clock when Chad contacted it. So what if nothing had happened to Chad, right? Then he really wouldn't have received any new information when they contacted again and Alice talked to them. So that's something you have to be kind of aware of. Now, the big takeaway here is vector clocks can induce an order that directly reflects causality. Event 1 happened before event 2 only if the vector clock 2 dominates vector clock 1. So I'll just kind of read this. Every event or update visible when event 1 occurred was also visible when event 2 occurred. So think about this. If all elements in A are strictly greater than B, right? So let's say in A we have 2, 2, 2 because there's 3 nodes, and B is 1, 1, 1, right? So that would be an example if all elements in A are strictly greater than B, or some elements in A do not exist in B. So maybe B has just not even gotten them, but all elements in B exist in A. Then we have this domination, which will then give us this order, this reflect this causality ordering that is so great with vector clocks. That's kind of a big takeaway here. So why have vector clocks? We've kind of gone over this, but like some real world uses is like distributed debugging. Uh, they kind of allow this ordering that might help you figure out why there's a certain bug going on in your code on this distributed system. You can investigate causal order, see if your system's holding true and operating correctly. And then just in general, distributed algorithms allow loads of information, or basically vector clocks allow you to do loads of distributed algorithms that you know you wouldn't normally be able to do. So great, thank you. If you have any questions, feel free to let me know. Bye bye.